Yeah, so we're going to talk about San Diego weather. So it's 70 and sunny every single day. Um, yeah, but there's a little more to that. So, uh, kind of breaking this up into four different sections. The first one is kind of the biggest one, um, talking about the basic patterns that we get and kind of some um, basic meteorology that's relevant to understand. And then the next section we'll talk about forecasting and like various tools to use. The section after that we'll talk, site specifics, how many of our popular spots are impacted by different weather phenomenon and what to look for. And then the last section will be site calling, kind of putting it all together and what to think about when making your call for where to go. There is a lot of material here, and I don't want to keep everybody super late, so I am going to ask that people hold their questions till the end. And if there are a bunch of questions, I'm free to kind of stay late for the people who also want to stay late, but I'm going to try to make sure that we get through the main presentation in a reasonable amount of time. So just write down your questions or post them in the chat as we go through, and we'll circle back at the end of the presentation to revisit material and answer questions. So we'll start by covering, what causes circulation aloft. I mean, this is really what drives the weather patterns, and it's all driven by the sun, and the areas of the Earth that get the most direct sunlight get the most heat. So at the poles, it's cold. At the equator, roughly, it's the hottest, and that creates kind of sea breeze like circulations where the hot air rises at the equator and generally tends to move towards the poles where it cools, goes downward, and circulates back. Also, the Earth is tilted, but it gets way more complicated than that because there's the Coriolis effect, because the Earth is spinning. Um, and really, the Coriolis effect is conservation of angular momentum. So as it goes towards the poles, the radius from the axis of rotation gets smaller. So it ends up having more momentum to the right. And so the rule of thumb in the northern hemisphere is the flows rotate right. So as the circulation aloft travels north towards the poles, it'll turn to the right, which is moving from west to the east. And the reality is by the time it travels about 30 degrees latitude, it's already made a 90-degree turn. So the flow doesn't go make it all the way to the poles. Um, and it kind of creates these regions every 30 degrees of latitude where something happens. So kind of near the equator, um, where it's getting the most heat, there's persistent low pressure. And then the air piles up at about 30 degrees latitude, um, uh, as high pressure, where that's where it kind of sinks back down to the surface after it's turned right. And then these cells kind of repeat each other. So some of that air aloft will then, continue its poleward journey. And at 60 degrees latitude, there's another low. Um, so so really the key takeaway here and what impacts the weather that we see is the high at approximately 30 degrees latitude and the low at approximately 60 degrees. And this changes throughout the year because the Earth is tilted. In the winter, it'll be 23 degrees off, and in the summer, it'll be, positive, 23 degrees the other direction. So the location of these highs and lows will vary throughout the year. And that creates what's known as the North Pacific High off the coast of California here. San Diego's at about 32 degrees, 33 degrees latitude. So that's one of the reasons why it's always 70 and sunny here, is because we're kind of located in where that persistent region of high pressure is. It's only during the winter when that high pressure moves further south and the low pressure at 60 gets closer to us that we actually get the storms. And so that's the Aleutian low, which is at off the coast at about 60 degrees to us. And these circulation cells are also what's responsible for the jet streams, as it's the air aloft making that 90-degree turn at 30 and 60 degrees that creates those jet streams. This slide kind of shows exactly those highs and lows that are most important to us. Most of our weather that we have is driven by these two highs and lows and kind of where they are. So during the summer, the North Pacific High kind of moves up into our region and deflects storms from getting to us. But during the winter, it moves further south and allows some of the troughs coming off of the low pressure systems here to get to us. The jet stream, you'll hear a lot about the jet stream and it impacting weather. That's due to these circulation cells that we were talking about, where at 30 and 60 degrees, there's generally flow aloft that's trying to get to the poles that has made a 90-degree turn due to the Coriolis effect, and you just get a bunch of air piling up and turning sideways, and so it gets a lot of momentum and just circulates around the entire planet. But it's not in straight lines. There's a lot of variation because the Earth doesn't get heated evenly. The main reason why the Earth gets complex weather is because the terrain is complex. A lot of the planet is covered in water, which doesn't absorb sun as well, and other areas are covered in land. Some of it maybe is green vegetation, which doesn't heat up as easily as, say, dry desert. So there's certain areas of the Earth that receive the sunlight better than others, and it's constantly rotating, and the tilt of the Earth is constantly changing. So the weather patterns are constantly changing and never able to find equilibrium. So that's why the jet stream and where all these circulations and highs and lows are constantly on the move. They're also responsible for trade winds, which aren't really significant to us, but at 15 degrees and 45 degrees latitude, there's trade winds on the surface due to these circulations, but us being at 33, we're kind of smack dab in the middle and we don't get trades. Troughs and ridges. I think this is kind of one of the key things to learn to understand. To see the big picture of what's happening. What the jet stream will fluctuate, as I said, due to just kind of random variations because the Earth is getting heated, very asymmetrically and dynamically. So just constantly the jet stream is kind of winding around like a snake, and it kind of forms waves. So they're called long waves. You can see top-down view, looking from the poles. Normally at all times there's about 4 to 7 they call long wave troughs. In this picture you can see 5 of them. Just areas of low pressure where the polar air mass kind of extends a little bit further down. And so those areas of low pressure where the polar air extends further down are what are known as troughs. And then the areas where the tropical the subtropical air mass goes upwards are what are called ridges. And generally the troughs are areas of low pressure, which generally are associated with cold, rain, wind, unstable, where the ridges are associated with stability, just generally fair weather, typically warm, right? The past yesterday was very high pressure day because a ridge moved over us, and you could look up and see clear skies and nice warm temperatures compared to what we've been having. And then I'm not going to get too technical in this one, but there are long waves and short wave troughs. The long waves are kind of the bulk movement, but sometimes there's what I call a trough within a trough. You can see in the illustration here where this was actually about a week or so ago, where there was a short wave that came right after the long wave. And the short waves often can be associated with like more severe weather. A lot of times when the low comes through, there's oftentimes many short waves kind of embedded on these long waves. And when the long wave moves through, oftentimes the storm bands follow where the short waves are. Sometimes you'll notice like the storm will move in with like lines, or it'll be a line of clouds and some rain, and then it clears, and then there's another line of clouds and it rains. Those are the short waves moving through. This is, you might be wondering what this is. I'll cover how to get this view later on, but this is what's known as the 500 millibar plot. So it's just kind of the winds and pressures at kind of halfway up the atmosphere. It's approximately 15,000 feet of elevation at that altitude. It's kind of the middle of the atmosphere as far as the boundary layer where all the weather happens. So it's typically convenient to look at what's happening at that level because it's less influenced by the terrain, and you can really see the big picture of what's moving through. Associated with these long wave troughs, there's typically a cold front because that the air in the trough is coming from the poles, and these air masses don't really like to mix. So when one of these troughs digs down deep to the south, it normally brings in some cold air, which brings a front. So when one of these fronts approaches, in San Diego, we typically see very predictable wind patterns. So before the front happens, we normally will see southwest winds, and that's just because the jet stream's pushing the storm systems from the west to the east. So the storms approach from our west, and the troughs, they're also coming from the north. So it's rare that we see something come from like the southwest or the southeast. So if the low, so flow around a low due to the Coriolis effect goes counterclockwise, and around a high it's clockwise. So in the illustration here, you can see the direction of circulation around a low. If the low is situated to the northwest of us, which it almost always is when the front approaches, the wind direction's going to be southwest, tangent to the illustration here. And then when the low pressure passes through, that's normally when we get all the rain and everything. Typically not always, but typically we get strong westerlies. So the winds turn from southerly to more straight in westerly, and they normally nuke really hard. And then after the front clears, we typically get a northerly component to the wind, just because as that trough has moved on, now we're kind of on the back end of this low, and the flow is circulating around on the north side of that counterclockwise circulation. And these fronts occur primarily in the winter, because as we talked about, you know, the tilt of the earth and how the North Pacific high and Aleutian low shift during the winter. The most sunlight is now to the south of the equator, and the spot getting the least amount of all those pressure systems shift south. So here's a case study of how you can use these 500 millibar plots to see what's going on. So this was a storm that hit a couple years ago, where I captured the 500 millibar winds and pressures for kind of each day leading up to the front and a couple days after. And what you can see is the areas of purple right here. This is the jet stream. So this is at the 500 millibar level. You can go into your windy app and change the altitude to 500. I think it's HPA, and HPA is almost identical to a millibar. So just set it to 500 HPA. You'll see this, and you can see where the jet stream is. And then as we get closer to the front, you can see how this trough starts to form. I would describe it as like digging in. This trough just starts digging its way down towards SoCal. And the day that it rains is the day where the axis of this trough passes through San Diego. So if you were to draw a line straight through this trough, and kind of where the pressure gradients are the highest down here at the bottom, that's going to be the rain day. And then the post-frontal day is going to be the day that this trough pushes through and is no longer there. So when you're kind of planning which day you might want to be sick at work, you can, the ECMWF is pretty accurate global model. And you can pull up the ECMWF and windy, and I think it's 10 days in advance. And just by seeing where the troughs are, you get a good idea which days you kind of want to earmark for flying, right? If I were to look at this forecast, you know, I would select, you know, that Friday is the day I'm calling in sick. Of course, forecasts can change, but these kind of global circulation patterns are generally less subject to the rapid change that we see when we're trying to tell if, you know, Blossom's going to have 2,000 foot or 3,000 foot top of lift. We can also look at the temperatures in the same way. So in the windy app, you can change it from wind to temperature. And you look at, this is the 500 millibar temperatures. So this is what the temperature of the air is at about 15,000 feet or so, middle of the boundary layer. And you can kind of see this trough forming through the temperatures as well, right? It really goes to show how, it's this cold polar air, which if you know anything about instability, I mean, think about the lapse rates you get when you get cold air advection that moves into the region. Not to mention the low pressure in the region causes the atmosphere to generally rise, right? Everything on the planet is constantly trying to reach equilibrium. So when you have a low pressure aloft, it's kind of like a vacuum, and the air underneath it will want to rise to fill that vacuum. So when that happens and the air rises, it cools. So that helps bring good lapse rates, and that's why pre and post frontal flying typically is some of the best flying we have, because it creates a very cold atmosphere. And when you do read the weather discussions, so we get into forecasting, I'll bring up the weather discussions, but NOAA does a very good job writing kind of technical weather discussions. And you'll see all sorts of talk about troughs and ridges. Oftentimes you'll hear them say high pressure, low pressure. I remember before I learned about this stuff, I would get confused because I would be looking at surface high pressure and surface low pressure, and I'd be like, what the heck are these guys talking about? That there's, low pressure, right? It doesn't do you any good to look at the surface pressures. It's the pressures aloft, typically at the 500 to the 700 millibar level, that are significant. So when you're trying to correlate what you're reading in the NOAA discussions, look at those levels aloft. So not all fronts will come in as troughs. Sometimes they'll separate from the jet stream and form what's called a closed low or a cutoff low. And typically that happens when a strong shortwave develops, because the shortwaves don't get pushed by the jet stream as much, and it can kind of pull the entire trough far enough away from the jet stream that it just separates and does its own thing. Once that happens, kind of all bets are off as far as the timing of what's going to happen with the storm, because these storms are very predictable when they're getting pushed by the jet stream. But once they're out, they kind of just meander around until something happens where they start getting pushed through and they get reabsorbed by the jet stream, or the pressure gradients kind of equalize and they just dissipate. But they can linger for several days. And they can even backtrack. Since they're not getting pushed by the jet stream, they could move from east to west. And so whenever you see a cutoff low, you kind of know not to put too much faith in the current forecasts you see, right? You go on your weather app and it'll tell you that, Saturday is going to rain. But then the next day you go and you check the weather forecast on your weather app for Saturday, and it says it's not going to rain. It's going to rain on Sunday. Or maybe it's not going to rain at all, or, all sorts of stuff can change. And that's just because the numerical models have a very difficult time predicting the movement of these cutoff lows. So really the key takeaway here is when you see these cutoff lows, there's going to be a question mark on the forecasts that you're looking at. And they could linger for a while. Instead of just being one day where the front pushes through and there's one day of rain, we could end up with 2, 3, 4 days of rain in a row, just depending on how that moves. And then occasionally last year we got a hurricane. So that's this picture in the bottom center. This is that hurricane that came in and gave us a bunch of rain. So that's one that came from the tropics and worked its way up to us. So not everything we see kind of comes from the polar aspect, but because we're high enough up in latitude and near a region of high pressure, normally those storm tracks don't make it to us. But yeah, we had that hurricane last year, and the year before that, we had a tropical storm. Maybe it was 2 years before that. So something to keep an eye on in the summers. And then talk about inside sliders and blocks. So this is a setup that we just had a few weeks ago. And that's where a high pressure forms to the north of us and doesn't let low pressure systems move through in their normal track, right? The high pressure here will deflect it and the low can't get through. So, but then, if the low starts to develop from a more inland track, that's called an inside slider. And there we're going to see kind of a different weather pattern. We talked almost all the fronts we see will have southwest winds when it's prefrontal, then westerly, and then it'll go northwest. But with these inside sliders, since the front's approaching us from the northeast, we're actually going to see northeasterly winds as it approaches. And then this one pinched off into a cutoff low, and then with the high pressure situated over it, that creates what's called a blocking pattern. And essentially what's happening here in this picture on the far right is that the high pressure here is deflecting the jet stream. So now this cutoff low is so far removed from the jet stream that nothing's pushing it, and it just sits there. So this one lasted for, I think, 5 or 6 days. So it was 5 or 6 days straight where it OD'd in the afternoon. It's kind of a blessing and a curse. The flying was great. We had, short windows. One of those days, Alex and I launched Little Black and flew past Blossom, but we couldn't get to Blossom because it was raining at Blossom. Connor made it to Sweetwater Res at the bottom of Mother Miguel. So it was a whole week where it was unstable. Right, the thermals were great, everything was fantastic, except for the fact that it would OD and rain out in the East Mountains in the afternoon once enough heating happened. So kind of a bittersweet condition. But in my opinion, it beats stability. Atmospheric rivers, this is a big buzzword that you hear a lot about, especially recently. So what the hell is an atmospheric river? It's a circulation of moisture aloft, where the river that we get they call Pineapple Express, because it comes from the tropics. It's typically around Hawaii, where the moisture gets kind of lifted up into the upper atmosphere by storms out there. And then once that moisture is aloft, if there's circulations aloft, just due to how the jet stream has traveled, that kind of pulls that moisture towards us. Then we get a bunch of really moist air coming in aloft. And then when that coincides with a low pressure, that creates a lot of lift. We get enough convection to cause rain, and it just rains a lot due to the high moisture content. So the way to spot these atmospheric rivers is precipitable water is what I prefer to look at. the unfortunate thing is the higher res models don't cover the globe. So when you're looking for atmospheric rivers, it helps to see what's happening out in the Pacific Ocean in the NOM3 and HRRR. You can't see that, but you can't see it on the GFS. I would love it if you could see it on the ECMWF, but XC Skies doesn't support the ECMWF, and Windy doesn't support precipitable water. But one thing that you can do if you want to look at the ECMWF is you can look at the dew points at various altitudes. So you can look at, say, dew point at 500 millibar, 700 millibar, and see areas. If you see a streak of water, streak of high moisture, kind of heading straight for SoCal, timed with a low pressure system moving through, you know it's going to absolutely dump, right? Versus one of the, we joke in San Diego, it doesn't actually rain, it just drizzles a little bit, drizzles for 20 minutes and then stops, and that's a day of rain. So how do you know when it's actually going to dump? It's look at how much water is in the atmosphere. And one thing to consider when we have these atmospheric rivers is that it could close some of our launches. So Horse is probably the main one where they'll lock the gate. You can still fly it, but you got to earn your turns and heights. Next topic is El Nino Southern Oscillation. So right now it's an El Nino year. So what the heck does that mean? I think a lot of people just understand that El Nino means it's generally going to be wetter. La Nina means it's drier. You need to distill it down to the very basics. That's pretty accurate. But what causes El Nino? So we talked about the circulations and trades. I guess the one impact that trades have on our weather here is the trade winds are responsible for driving El Nino and La Nina. So when the trade winds blow across the surface of the Pacific, which is a massive boundary of water, it actually pushes friction between the air and the water. It actually pushes the water from the east to the west end of the Pacific. So when those trades are really strong, it leads to a piling up of water out in the western side of the Pacific. And then when that happens, it creates upwelling near California. That's why our water is so much colder than, say, North Carolina's water, even though we're at similar latitudes, is when the wind is pulling the water away from the shore, the circulations in the ocean that's set up is it actually brings water from deeper down in the ocean up to the surface to then provide that flow of water that can head out to the west. So that's a phenomenon called upwelling, and that leads to cold water being formed off the coast of California, off the west coast of Baja and California, and warmer water here. Well, that creates its own little kind of sea breeze like circulation, where that kind of fuels it even more. So the trade winds create that piling up of warm water and this piling up of cold water. That creates its own circulation that then strengthens the trade winds and makes that even stronger. So that's what's known as a La Nina condition, is when those trade winds are exceptionally strong and the water in the Eastern Pacific is exceptionally cold. And actually what happens is the elevation of the water in the West Pacific gets measurably higher, several feet higher than in the East. And so eventually when something happens due to the circulations aloft, something happens that kind of causes those trade winds to slack off a bit. Now you have a huge pile of water at a higher elevation than the other side of the ocean, and and all that hot water flows downhill back towards um, the east side of the Pacific. So you just get this pocket of very warm water that gets closer to, say, California. And what that does is now you get more moisture close to California, helps trigger the storms more. So that's the reason why during El Nino we tend to get more storms. That said, it's not guaranteed. Just because it's La Nina doesn't mean it's going to be um, a dry season. And just because it's El Nino, doesn't mean that it is going to be wet. In the images on the right here, NOAA has kind of broken down, classified each El Nino and La Nina season as being wet or dry. And generally for El Nino, it tends to be wet, but for La Nina, I mean, looks like 1/3 of La Nina years end up being very wet seasons. So just because it's La Nina doesn't mean that it's going to be dry. But in general, if you hear that it's going to be El Nino, you can expect it to be a little wetter. Then we got the sea breeze. This is probably the dominant microclimate effect that influences our weather in San Diego. And what this is, we got a cold ocean off our shore, and then we have land that gets heated more readily by the sun inland. And so it creates a little heat engine where the land warms up during the day, which creates a heat low as that air rises. So the hot air rises, creates a heat low underneath it. That heat low underneath it draws in the cooler air from the sea. At some point aloft, it circulates, returns, and it drives itself. And that's why almost every day, unless it's Santa Ana's, we have a westerly prevailing wind, and it's generally quite strong midday, especially during the summer. Yeah, because a lot of it has to do with the temperature differences. So during the summer, that's when the land gets the hottest. And the Pacific Ocean will get warmer, but I mean, the Pacific Ocean never really gets that warm. So you get the highest temperature differential between the land and the water during the summer. And this can create convergence if there is an opposing easterly flow. If the general flow aloft is westerly, it's probably just going to be strong westerly winds all the way out through the desert. Summertime stability. So you'll hear a lot about, the inversion. The reason why it's so significant in San Diego is because it's an artifact of the fact that we have such great weather all the time. Because we are at about 30 something degrees latitude, we're in that area of persistent high pressure. So during the summer, the North Pacific High just really dominates things and leaves us in an area of persistent high pressure where we have no low pressure systems that can get through during the summertime. And when there's high pressure aloft, it wants to escape and it compresses all the air underneath it. And when the air compresses, it heats up. It's the exact opposite of when a thermal rises. When a thermal rises, it expands. When it expands, it cools. It's the exact opposite of that. When the high pressure presses down on the air underneath it and compresses that air heats up. So when a high pressure aloft comes in, it generally warms the entire atmosphere, and the warming happens from the top down. So that makes it very stable aloft. And then at night the ground will get cold, and there will be some circulations that form at night, kind of creating a boundary of cooler air underneath, that then once the sun gets on it again, now you have an unstable layer capped by a very strong inversion. And typically during the summertime, we find that inversion around 3,000 feet, which has a big impact on our flying. That's why, unless you can hop in a convergence, that your thermal flying is typically limited to altitudes of about 3,000 feet. You go fly Palomar in June, you'll realize that pretty quick. So to remove this inversion, you really need a change to happen. You need a front to move through or something to refresh that lapse rate. That inversion then leads to marine layer clouds forming during the summertime. And that's because we have warmer, dry air flowing over the cold ocean, so it picks up some moisture. That air then can rise up to where that inversion is, and if it's moist enough, it'll form a cloud. And then the sea breeze. So then when the land heats up and it creates a sea breeze, it'll pull those marine clouds inland. That's why oftentimes you'll see the marine layer go all the way up to, say, Rainbow Pass, near Palomar, but it'll be clear and sunny in Temecula. And that's just because it kind of gets boxed in, and the inversion taps it, and prevents the land and the inversion kind of separate those air masses. And when the pressure aloft is higher, you might see that marine layer disappear. You might see the marine layer clouds disappear, because it heats things up, and now the dew point's not reached anymore. Doesn't mean it's any less stable, but at least some more sunshine gets through, so you might have stronger thermals, underneath that inversion. And these marine layer clouds typically are the strongest in the spring, because that's when that's when you start to get these temperature differentials between the land and the ocean. This graph right here is showing that temperature, the sea surface temperature. This is the average Pacific Ocean temperature in Celsius. So kind of in this May-June time frame, that's when we really start to see those get the marine layer come in, because the land is getting warm, the ocean's still somewhat cold, but then once the summertime hits, the land's getting warm, it's creating a strong sea breeze, but the ocean's warmer. So we don't see as much marine layer cloud. Then there's the Catalina eddy, which can happen and kind of throw curveballs into things. And typically what we experience on Catalina eddy days is strong southerly wind, southwesterly, or even southerly, southeasterly sometimes. And a lot of cloud cover some days. And what happens is we have the Channel Islands, including Catalina, sitting off the coast, and it kind of creates a vortex and spins that north flow. So it's kind of counterintuitive, but on Catalina, because on Catalina Eddy days, we see south wind in San Diego. So when we're doing our forecasting, everything looks south. But really what's happening is there's a lot of north flow that day. In order for the Catalina Eddy to happen, it needs to be north flow coming down the coast. And the researchers are still, debating over exactly what condition will cause Catalina Eddy. There's some theories that it has to do with where the upper level troughs and ridges are, coinciding with that north flow. But the one thing that is clear is that it takes strong north flow ripping down the coastline. But the key takeaway here for our flying is on these Catalina Eddy days, expect there to be very southwest wind. And I typically find that the wind is stronger than the models predict on these days. And one way that you can tell that's going to be an eddy day is if you look at like a streamline representation of the wind in say XC skies or windy. You can see how the north flow is going down the coast, and then it makes this vortice. It's one way to identify it, and the real way to confirm it in real time, if there's clouds, marine layer clouds, is you can look at the satellite imagery, and then you can tell on the satellite imagery in the morning that those clouds are just getting kind of circulated around in kind of a circle, and you can expect stronger winds that day, maybe some extra cloud cover.
Let me just kind of add a quick little note there
Yeah,
on Catalina Eddy. So, and give Rob a little bit of a breather, maybe grab a glass of water or something.
Yeah.
Been talking a lot. So this is all great, Rob. Anytime there's small craft advisory or high winds predicted from Point Conception to the Mexican border, and so that'd be the offshore winds prediction, and or from Point Pedras Blancas down to kind of Point Conception. So anytime, so that'd be like up near San Luis Obispo, north up at San Simeon. So all the winds that are coming down the coast, and it's typically in the springtime, is when they're start really ripping, then also in the summertime. So strong winds out there create and set up the Catalina Eddy.
Thanks, Steve. That moves us into the next slide here, which is about the Great Basin, which isn't really a weather phenomenon, but it's a geographic feature that is responsible for quite a bit of the weather that we see in San Diego. So this is the largest watershed in North America. So it's got no outlets, completely boxed in by mountains. So any rain that falls anywhere in this Great Basin kind of drains to somewhere in the middle of it and evaporates out. Doesn't make it out to the ocean. And this is kind of a desert area too. So it's a lot of just barren land that can absorb heat readily, and it can also release heat readily. So during the summertime, this land gets extremely hot, and during the wintertime, this land gets extremely cold. So what this does is it creates large temperature differences between the Pacific Ocean, which does get a little hotter and a little colder depending on the season, but generally stays much more moderate temperature. So the temperature difference between the Great Basin and the Pacific Ocean will drive two of the feared phenomenons for pilots in San Diego, which are the monsoons and the Santa Ana winds. So the monsoon pattern, this is what we're going to see in the midsummer in a couple months here. Happens every year. It's when the Great Basin gets really hot, and so a lot of thermals go up, and it ends up creating a piling of air aloft over it. So you get a high pressure aloft. It's a heat low down at the surface. At the surface level, it's a low pressure, but up aloft, it's a high pressure as all that air moves from the surface up to aloft, and it kind of pulls in the Bermuda high a little bit. And sometimes it can reinforce that Bermuda high and pull it in up to here. The end result is when you get a high pressure aloft sitting right here over the Great Basin with San Diego sitting in like the southeast part of that circulation, what's going to happen is it's going to pull in tropical moisture from the Gulf. Um, and this moisture is traveling a fair ways. So I'm sure it rains in Texas and gets drier down low, but once it hits, say, our Laguna Mountains, and there's a convergence that goes up to 14,000 feet, um, the moist air aloft that's present there will get lifted, and once it starts to condense, it'll cool at the moist adiabat lapse rate rather than the dry, which means that for every 1,000 feet that parcel of air rises, is cooling less. So once you trigger that deep convection, depending on the lapse rate of the upper atmosphere, it could go all the way up to the stratosphere at about 30, it's approximately 30,000 feet. That's where the troposphere ends. The troposphere is the boundary layer where all the weather happens. Up above that is another layer of the atmosphere called the stratosphere. And there is a very deep inversion there, and the stratosphere actually gets warmer. The whole stratosphere is inverted. It gets warmer with altitude. So no storms can really penetrate into the stratosphere. That's why you see the anvil heads on cumulonimbus clouds, because once they hit the stratosphere, they can't rise any higher, and so they just have that flat anvil head. But the point is, it'll be very, very dry air near the surface and up to decent altitudes. But then aloft, there's all this moisture. So it generally won't rain at the coast unless the storm gets triggered and then the winds aloft blow it over to the coast. The storms will primarily get triggered over Mount Laguna, San Jacinto, Gorgonio, Hot Springs Mountain, some of the bigger trigger points in the convergence. And what this means to us is these storms can be quite dangerous because it's the perfect recipe for a gust front. When you have dry air underneath a wetter air mass, then when that cloud that forms at, say, with a cloud base of 14,000 feet, when that overdevelops and starts to rain, the rain will evaporate before it hits the ground. That creates what's called virga. And when that rain evaporates underneath the cloud, it gives off or it takes latent heat of evaporation, which essentially cools all the air around it. And so you get this pocket of air where the virga is that gets very cold very quickly. Cold air is more dense than warm air. All of a sudden, all that cold air just falls out of the sky and kind of slams into the ground and then fans out, and you can get winds. We experienced a gust front after I bombed out at Elsinore, and Catherine and Alex flew to Saboba, and I went and picked them up. We knew the day was going to OD, so we had a short window. We were trying to make moves quickly because we knew that we didn't want to be in the air after 2 o'clock. They make it to Saboba. We go get uh, you know, tacos afterwards, and I think it was around 3 or 4 o'clock. We walk outside and it's just blowing 40 miles an hour and just super gusty. Palm trees are getting bent over. You not want to be in the air for that. So that's the real fear of these tall clouds that happen during monsoon season. Of course, you would never want to fly underneath them, but even flying in the vicinity of them can be dangerous. You have to think about where the outflow is going to go. Um, uh, uh, it's most dangerous to be in like a narrow valley. If the gust front drops out while you're in a narrow valley, that energy doesn't fan out, so it stays just as concentrated, you know, far away from the cloud as it was close to the cloud. So say you're flying Palomar and you see a big thunderhead forming over Hot Springs Mountain, that you're not like, I can guarantee you're not going to get sucked up into the cloud that's over Hot Springs Mountain while you're at Palomar. So the cloud suck probably isn't going to be a danger. The real danger is if that thing drops out, um, and that outflow shoots its way kind of through Warner Springs and into that valley. And once that air is getting funneled through that valley, it's not going to dissipate until it, gets to kind of the 15 freeway where it can fan out a bit more. So for monsoon days, big thing to look at is precipitable water. So in XC skies, I pay close attention to, if you see a bunch of red, that means there's a bunch of water in the atmosphere. You might be dry at the surface, but there's a lot of water in the atmosphere. Look at cloud depth, right? If the cloud depths are 10, 20,000 feet, you should be concerned and pay attention to where those clouds are. And CAPE. CAPE is convective available potential energy. The bigger the number, the bigger the potential for storms. And so how do you know when it's going to be monsoon or not? You can pay attention to where the high pressure is and then what the circulation aloft is. So when you see the more southeasterly circulation aloft due to a high pressure here, you can suspect it's probably going to be monsoon. When that high pressure repositions itself and we find ourselves more in southwesterly aspect of that circulation, that'll be post-monsoonal. And those are really the days we're trying to target. So likewise, when we're talking about frontal passage, you can kind of do a similar predictions. So this was July 31st of last year where we had just a massive monsoon event. I think this day the storms blew up so much and the winds aloft were eastward enough that it just rained buckets at the coast after those storms got blown over. So what you can see here is a ridge. So we have a ridge of high pressure, but right now we're still in the southwest flow. So we're not really getting too much monsoon. As the high pressure shifts, this next day on the 30th, we're getting south-southeast. So we're getting more moisture. This would be what we call pre-monsoonal. And then on this day, the winds aloft went east-southeast and it stormed. And then the next day, the high shifted over further to the east, and that put us more in a southwesterly flow, and that brought in drier southwest winds aloft and cut off the monsoon flow. I talked about how I like to look at precipitable water. So here's a case study for those exact same days. So the first days where it was more southwesterly, you can see kind of the greens and the yellows are lower precipitable water values, and then the oranges and the reds are higher precipitable water. So when the more easterly component, you also see in XC skies here, I have the winds at 12,000 feet shown here in each of these images. So you can see the wind barbs to also see how the precipitable water coincides with that wind direction. So on the day of the major monsoon event, you can see how easterly those winds aloft were and how strong they were. And then the amount of water in the atmosphere. And these reds are like 2 inches of water that's integrating the water throughout the atmosphere in the column. And then when it goes post-monsoonal, that all that moisture that was brought in doesn't just disappear overnight. It's got to get kind of pushed, circulations aloft have to move it out of the area, or it has to rain enough that it kind of falls out of the atmosphere. So on these post-monsoonal days, there's still a chance that they could OD. So you got to pay attention. But that's really what we're looking for, because it's the days where you're going to get the big puffy clouds to show you where the convergence line is, but not form a thunderhead that'll kill you. And then here I have an example of the weather discussion. I'm not going to deep dive too much into this, but on these days, what I encourage people to do is read this discussion all the time, and then take kind of the knowledge that you're learning with these mechanics to, once you understand all these concepts, what they're saying here will start to make sense. Here where they're talking about southwest flow aloft, a drier southwest flow aloft will lower the thunderstorm threat, whereas on other days here, they're talking about the steering flow from the south. It's all tied into those concepts. Last slide on monsoons. This is kind of important when you're forecasting during monsoon season. Also relevant during the winter for frontal passages. It's just the cloud bases are much lower and the air underneath is wetter. But my favorite tool to kind of spot where the ODE is going to happen is to look at cloud depth. So you can set your XC skies to look at the depth of the clouds, and where you see these reds are like 20 to 30,000 foot tall clouds. Those are thunderheads. So you should be careful. And you also might notice when you're just looking at the top of lift in XC skies that you'll see these anomalies where it's like, why the heck is there like a big blue hole in the middle of the convergence line right here? What's going on there? Well, what's happening is if you rewinded and you went to the 2 o'clock forecast, it would have it shows a 30,000 foot cloud sitting right there. So what happened is this drops out, and the model is predicting there's going to be raining buckets right there with gust fronts, and you can even see the outflow sometimes. So this picture right here is that story I was telling outside of Saboba. I have a video of it, but this is a screenshot. The video is pretty gnarly. Even the photo, you can see all the dust in the air. And so this is actually this picture on the far right is actually the forecast for that day. And you can see it's got tall clouds predicted. If this was rewinded, it would have shown the tall clouds kind of where this red circle is, but at this time it's predicted that it's dropped out. You can just see how strong the winds are, right? It's like, why is it saying that the winds are strong? Well, it's because it's predicting that there's going to be a thunderstorm there. So that's things to look at. I also like to look at precipitation. And, you know, on this case study on the left-hand side, right, you can see that the pocket of, you know, random sinky hole coincides with where the tall clouds were, also coincides with where the precipitation is forecast. And then you can also look at surface gusts, and you'll notice in the same regions, see strong surface gusts. That's the outflow, where the gust front drops out. And this day ended up actually, so interesting fact, this day, the case study on the left actually ended up not ODing. We looked at this forecast and we decided to give it a go. A couple experienced pilots, I think it was me and Chris, and we decided that we were going to be on the ground by 1 o'clock. And we figured that was enough time to launch Laguna at like 9 or 10 in the morning and get to at least like Warner Springs. If we moved fast enough, maybe we could get to Palm Springs in time before it OD'd. So we were going to give that a shot. We showed up and Laguna was blowing down all day. So we didn't even get off the hill until 12:30, 1 o'clock. But what happened this day is there's thunderstorm over Ensenada at like 7 or 8 in the morning. And when that thing dropped out, and with the wind direction aloft, kind of being southerly, a little southwesterly, it blew all the debris from that cumulonimbus that dropped out into the convergence, and it essentially just shaded everything. And so what that did is it blocked the sun, so then it limited the amount of sauce, and then it prevented the entire convergence line from ODing the entire day. And this was actually a day we were finally able to get off launch, and then it was good all day. Clouds weren't getting too tall, and I got into Borrego Springs and got to climb to 14,000 something feet and hopped over kind of Toro Peak into Palm Desert. So, you know, the forecasts can say a bunch of information, but sometimes you got to just monitor how the day develops, because at the end of the day, they're just forecasts. And the hardest thing for the models to predict is the clouds. And so if the model predicts the cloud development incorrectly, you can count on pretty much that model not being correct if clouds are going to be a factor. Next phenomenon here is Santa Anas. So the Santa Anas occur during the fall and the winter. And it's also related to the Great Basin. It's the opposite of that. During the winter, the Great Basin gets very cold. So that creates a piling up of air as the kind of air descends in the Great Basin. And then once enough pressure builds up in the Great Basin, it just kind of overflows and spills out. So really what drives this is surface high pressure. It's a pressure difference between the Great Basin and the Pacific Ocean. That's what drives that Santa Ana. And then the path of least resistance for that flow to get out is kind of going through all the mountain passes in SoCal. So the kind of the 8 corridor, from Palm Springs, Banning Pass, Home Pass, the Grapevine. That's where these winds are taking the path of least resistance, and then they'll spill over the back of all the mountains in between. But this is cold air, but since it descends from the high desert down to sea level, it actually expands as it falls down. So we experience it as warm air. And kind of the key takeaway here is that these winds can be very strong, unpredictable, gusty. So they're quite dangerous. And you need to be really careful flying in Santa Ana's, um, especially the stronger ones. And the major events are also fueled by circulation aloft. So if you get a high pressure aloft um, over the Great Basin, that then adds fuel to the fire, right? And further compresses air down in the Great Basin and enhances the surface high. So the best way to predict Santa Ana's, other than just looking at surface winds, um, is to look at the surface pressure. And so this is a case study a couple of years ago where we had a massive Santa Ana event where it was just nuking offshore winds at the coast all day. It resulted with this very high pressure forming over the Great Basin with a lower pressure out over the coast. And then you can kind of see the days before and the days after. It was a mild Santa Ana on the day before that major event, and then it was a switch day the day after. And this one of the reasons why it got so extreme is because this ridge formed over the Great Basin to help compress that air. So you can pay attention when you're doing your long range forecasting, you pay attention, especially during the fall and the winter, when you see these ridges forming over the Great Basin, you can also check the pressure, and regardless of what, the surface wind models are saying, you should be skeptical, right? Because the surface winds are influenced by so many factors, topology, and things can change so much. The circulation aloft those models don't change as much. So if you see this pattern set up during the time of year that's conducive to Santa Ana's, you should be keeping a lookout. So, but you can look at the surface winds and you will see the outflow. Kind of the main spot you see the outflow is down the Gulf of California, because that's one of the easiest places for that air to escape. So you see high northerly flow there. That's really what the kite surfers are looking at down at La Ventana is for that north flow to break through. But yeah, lots of tools you can use. Last kind of weather thing here is it's not exactly weather, but it influences the weather, and that's fire season. So when in the late summer and early fall, when things start to burn, and unfortunately coincides with Santa Ana season, we can get some large fires that then create a lot of smoke. The models aren't predicting that a fire is going to break out and block out some of the sun. So on days where, there's some smoke haze, you can lower your expectations accordingly and check the satellite imagery to kind of see what's getting blocked out. And you also really need to pay attention to TFRs because they might be bringing an aircraft to dump chemicals and water on it. So check sky vector to make sure there are no TFRs in place. Also, there might be road closures. Horace, Elsinore, and Marshall, sometime, if it's a bad fire season, you can expect those to be closed all season. All right, that took a while. Yeah, I don't know if people want to take a break or keep going. I don't know if we'll have to split this up into 2 sessions or not, but Steve, any feedback on taking a break or just keep chugging?
Yeah. So why don't you stand up and get some water? So it's 8:20 now. I think we can probably go another half hour before we start losing people, or they can probably go to 9:30 typically. Would be probably okay. But looks like we have lost. Actually, we're still up to 30 participants. So
Oh, did I put
just
everybody to sleep?
yeah, no. So kind of a quick comment on the Santa Ana. So it's not only just high pressure over the Great Basin, but it's also, as Rob kind of semi mentioned, it's the cold air So a combination of it being really cold in the Great Basin areas, coupled with the high pressure, um, and the flow gets created when the ocean temperature is relatively warmer than those cold temperatures over the Great Basin. So that kind of helps create and fuel that fire, or at least the wind direction, or the wind strengths. And so that air starts out as being super cold, and sometimes we do get cold Santa Anas. But and what happens is as that air starts moving through the passes and canyons, it's really cold and dense. So it's not, it wants to kind of seek the ground. But what warms that up is the actual friction of the air against itself. And that's what warms it. And sometimes in some of the really violent Santa Anas, you'll feel warm puffs along with cold puffs. So that's kind of points out, and that's kind of creates the real gusty factor, is that, the friction's heating and it's mixing with the cold. So it kind of becomes a real chaotic, nature of that Santa Ana. So if you're really interested in Santa Ana's, we have an article that links to a bunch of other articles and some videos on the Santa Ana phenomenon. So that's on the club website under just kind of do a search under the blog sessions for Santa Ana.
Thanks, Steve. So now let's jump into forecasting. For forecasting, we generally like to use a lot of different models. And I think it can be overwhelming to a lot of people, because there's so many options. I mean, if you want to distill forecasting down to, the absolute basics, I mean, get XC skies, look at the NOM3 and the HRRR, and look for, high altitudes and light winds, right? And you don't need to know any of this other garbage. Um, and to some extent that's true. When we're site calling, that's what we're doing, but there's a lot more to it. So with all these models, the two of these are, I would say, are the main global models, and that's the GFS and the ECMWF. These are models that are run over the entire planet. So it simulates the physics of what's happening across the entire planet. Whereas the NOM and the HRRR, they're focused on the continental US. So it's a much smaller domain. So they're able to refine the grid a lot more to get higher resolution and make the model more accurate. And then they take kind of inputs from the more coarse global models to create the boundary conditions to run those more high res models. But there's always a trade-off with computational power. They already have supercomputers running these, so they need to make sure that the number of calculations that has to be done is something that's practical and can be done in an operational amount of time. So that's why, it would be fantastic if, the NOM3 existed across the entire planet and they ran it 10 days out. But they don't do that. So they run these global models, 10 days out, and, but they're a lot more coarse. And then some of these other models, the Icon is another big one, but it's really more of a European global model. But it can help to kind of lump in on the same level as the GFS and ECMWF. There's the RAP, which kind of predated the HRRR. It's also an XC skies. I never use it because it doesn't really offer anything that the other models don't. I mean, really the only purpose I would see of it is to use it as another corroboration point to see if all the models are saying the same thing or not. Then there's the RASP, which is not ran by NOAA is actually a sailplane pilot up in NorCal a while ago who got hurt. And his job, he was a professional meteorologist. And when he was bored, not able to fly sailplanes, he created the RASP. So we benefit from that. And this is a high resolution model of just SoCal. That's available to us. And then I also have mentioned here the weather flow WRF model, the wind alert slash iKitesurf apps. Essentially, they are the same app owned by the same company with same interface. They just market iKitesurf to kite surfers because kite surfers like to use an app that says the name kite surfing in it. That's the exact same app as wind alert. They actually do have their own wind model that they run privately outside of NOAA. All these other apps, when people ask you, oh, what app do you use for the wind? It doesn't matter. Those apps, they're pulling data from the same place. Really, you should be asking yourself, what model does this app use? Because the various government agencies, and in some cases private agencies, will run these numerical models. And then these apps just are ways to visualize the data coming out of those model runs. So XC Skies doesn't run any models. All they do is pull in the data from external sources. Same thing with Windy, Wind Guru, like I said, the only exception that I'm aware of is Wind Alert does run their own WRF model. And I kind of already talked quite a bit about what makes a model good. The biggest thing in my opinion is the resolution. Essentially, to run these models, you have to divide the entire planet or a smaller subsection of it up into finite element grid, and the smaller those grid spacings are, the more accurate it's going to be. I mean, think like even we consider a 3 kilometer grid to be a high resolution model, but I mean, think about the size of Blossom, right? Blossom is just 1 or 2, grid points. So that's why those models can't resolve what's happening in the Blossom microclimate, because Blossom is just 2 points on the mesh that they're running. So so that's one of the main reasons why the GFS is kind of garbage when you're actually trying to make a weather call. But if you're trying to get an idea of if 5 days from now is going to be good or not, you're going to use the GFS because it's less computationally expensive, so they can run it more days out in the future. Another thing that makes the models good is, what are the inputs to it? If the model has the wrong initial conditions, then it'll calculate the wrong result. So some models will assimilate live wind data from weather stations. Some models will, incorporate the radar. So when they run the model, it knows exactly where the clouds are, whereas others maybe will just use, kind of the past model run or, and we'll get into it, but really the HRRR is the most advanced weather model in the world right now. And then the boundary conditions also, so the NAM will actually, it uses the GFS to calculate what's happening on the entire planet. And then if the NAM3 is only ran over this box right here, it'll take, whatever the winds and the pressures and everything, moisture levels, everything is along this line, it'll set that as the boundary condition. And then the initial conditions for the run will be, what the GFS output, and then it'll just kind of enhance the resolution, and maybe with some upgraded physics as well. And then also, how quickly does it update? So a lot of people think that the models only update twice a day. No, that's just XC Skies. And XC Skies actually does update the HRRR 4 times a day. But the HRRR actually updates every single hour. NOAA updates it every single hour. It's just, I don't know, maybe we need a generous donor to um, uh, contribute to XC Skies to upgrade their computers to so that they can pull updated HRRR information in every hour instead of 4 times a day. But coming out of NOAA, they're doing it every single hour. And the NOM3 is actually every 3 hours, I believe. But in XC Skies, we don't get it that frequently. So digging into XC Skies, I mean, this is the best app. It's not an app, but it's a website. And it is a subscription model, but it's not that expensive. And if you're a paragliding pilot and you like paragliding a lot, like you need this. This is not something that you should skimp on. This is the primary tool to try to figure out where you're going to go fly. And like I said, they don't run their own models. They just pull stuff in from NOAA. You can change that model here. You can change the altitude to kind of see what the winds are doing at different altitudes. The little hamburger icon here, you can change the parameter. Right now it's showing top of lift, but you can have it show clouds, updraft velocities, cape, precipitable water, whatever you want to see. Change time and dates. Important thing to note is you can change your settings. And one thing that I see people screw up all the time is their time zone. So especially recently we changed daylight savings time. So now we're -7 offset, whereas we were -8 before. And if you forget to do that, you'll be an hour early or late um, to launch. And the parameters I like the most, everybody's got their own preferences, but I typically find myself looking the most at top of usable lift, updraft velocity, cumulus cloud base, cumulus cloud depth, and the percent cloud cover. And always make sure to look at winds aloft, not just at the surface. XC Skies does have this cool top of lift feature, which will, instead of providing the winds at a certain altitude, it'll kind of dynamically give you the wind at whatever the top of lift is there. So it's kind of a quick button to just see what's happening aloft just in one slice. Couple tips on XC Skies. Everybody has their own preferences. I'm by no means saying that my preferences are better than others. Normally what I do is I just like to page through the time duration. So I like to look at the map so I can see the full spatial variation. And then I just hit the next button to kind of see how it changes with time. And I generally will focus on what's happening at like 1 or 2 p.m. Around peak heating just to see what kind of day it is. Also, I like to fly midday. If you don't fly midday, you're probably you should be looking more at like a 4 or 5 p.m., a few hours before sunset, for the glass off. And many people like to drop points. You can do this point cast and then you can kind of see what's happening at that point over time, right? So you can kind of choose how to slice it. Do you want to have the full spatial variation in your field of vision and have to page through different times, or do you want to have the entire time field in your field of vision and have to, poke around at different points? My preference generally is to look at everything, but I know like Chris loves to do the point casting, and it has its benefits. The thing that I don't like is, the model might say that right here, right at this point, it's not good, but it's could be good, just on the other side of the canyon or something like that. And especially, yeah, so yeah, you got to be careful where you drop your point, and maybe you want to probe around a couple points. But it is nice, you know, you can see in this specific example, right? Palomar looks like shit for a few days, but then all of a sudden, you know, this Tuesday looks pretty darn good. Um, so it's one way to visualize the data.
Why don't
Uh,
you go,
go ahead.
why don't you go back to that point cast real quick?
Yeah.
So one thing you can also note is the cloud formation. Why don't you talk about the clouds that you see in the point cast?
Yeah, I have a whole slide on clouds.
Perfect.
Yeah,
We show the point cast. Okay.
yeah, like I said, I don't really use the point cast much. So I can't, I generally prefer to look kind of in this layer, but like a tip that I can't stress enough is pay attention to the clouds. I can't tell you how many times I've been skunked, you know, with high expectations. Um, and you know, the models are predicting high top of lift, and then you show up to launch and there's a layer of high clouds blocking out the sun and you have mediocre flights. So one of the things that I recommend doing is starting by looking at the cumulus cloud base. If you turn on cumulus cloud base and you see color, that means that you can expect there to be cumulus clouds. And then whatever color it is, that tells you how high the base is. Um, so make sure the cloud base is high enough for what you're wanting to do. Um, and then you can check cloud cover. So if nothing shows up on cumulus cloud base, you have no color on cumulus cloud base, but then you switch to cloud cover and it shows that there's going to be clouds. You know that those aren't cumulus clouds. So that's how the primary tool that we use to determine whether or not there's going to be high clouds. Um, so you know, if they're cumulus, they're coming from a thermal. Um, and so we kind of like to see a bunch of cumulus clouds. But if there's no cumulus and a bunch of cloud cover, those clouds aren't coming from thermals rising from the ground, so they're not going to give us lift. All they're going to do is block out the sun and make our thermals less strong. And I found in particular the HRRR is very good at predicting those thin high clouds. And you'll often see it'll HRRR will show it as 100% cloud cover. And I found that the NOM normally misses those. And one thing to note about the HRRR is that it was designed for predicting thunderstorms. That's the whole reason why they got the government grant and they spent all of our taxpayer money developing this updated supercomputer model, even though we already had models, was to help predict severe storms. So we talked about horizontal resolution. These models also have vertical resolution, you know, how much they're resolving the atmosphere by altitude. So the HRRR has better vertical resolution. So that's because it's programmed to do very accurate convection calculations, which is what's going to spur, you know, a lot of the cloud development. So since clouds are the hardest thing for a model to predict, if the model gets the clouds wrong, then it gets the heating wrong, which means that the winds will probably be wrong, which everything's wrong. So uh, so if there's like a cloud day, I pay particular attention to the HRRR, but you never trust one model. You look at multiple models and see if they're all saying the same thing. And the more the models are all saying the same thing, the more confidence you have in the forecast. If the HRRR and the NOM are saying different things, it's a coin toss. You might, you know, say, oh, you know, trust this model a little bit more, but you got to be honest with yourself that it's more of a go to no situation. I don't know if you had anything you wanted to add on the point cast about the cloud, Steve. Otherwise, I'll move third tip here. Um, Pay attention to updraft velocity. This is how fast you can expect the thermals to be rising. Because a lot of times you can be hyper focused on how high you're going to get, but some of the best flights that I haven't been getting stupid high. It's just everything being super unstable, and you go on a glide and you get a climb right away. Then you go on another glide and you get another strong climb right away. Sometimes like Santa Ana days, you get really high, but then uh, a bunch of sink in between, and uh, generally the unstable days tend to be the best. So seeing uh, like 500 to 600 foot per minute everywhere throughout the county, it's like I don't necessarily care how high the top of lift is. Um, you're gonna go far. Another tip is you can only do this on a desktop. I strongly prefer and almost exclusively use my cell phone, but unfortunately, there's no way to see this with the mobile version of the website, and I haven't been able to get the desktop version to load on my mobile phone. It just always, even when I click view desktop version, it still doesn't give me this interface. But if you open up XC Skies on a computer, you can click this little eye icon right here, and then that'll tell you the last time the model updated. So kind of the conventional wisdom is during daylight savings time, we do our forecasting at 9 a.m. and 9 p.m. During standard time, we do it at 8 a.m. and 8 p.m. because that's a time where generally all the models have recently updated. We'll call it the morning update and the evening update. Um, and but it's not necessarily true. These models are updating constantly. Um, and so if you want to see whether or not it's updated, you can just go to here and you can see, okay, the HRRR at, for tomorrow updated up until 7 UTC. It was it's fresh, but it's an older run, going out here, and you kind of see it's just rolling through. So pay attention to when the last time XC Skies updated. Windy is the next most useful app that I find, especially I think the most powerful thing that it has that XC Skies doesn't is the ECMWF. This is by far the most robust long range forecast. So like when I put together those, full week forecasts, where it's like Monday this, Tuesday this, Wednesday that, for 7 to 10 days in advance. What I'm doing is I'm looking at the ECMWF 500 millibar level. And I'm just looking at where the troughs and the ridges are. And then based on, the kind of the time of year and the patterns that we could expect, I have a pretty good idea of what's going to be going on. So in windy, a couple things to note is you can, click on a point, and then you can click this wind button here, and then it'll kind of overlap all the models that it has. So you can kind of see how well they agree with each other, especially useful for forecasting a ridge site. You can see here, trying to forecast. I think right here, I was trying to forecast if I could fly like a mini wing at Torrey Pines. So very useful to compare all the models in one spot. One thing that people might not know about, there's the slider right here where you can adjust the altitude. So this is what you could slide to 500 HPA if you wanted to see what was happening at the 500 millibar level. And then you can change the model that gets displayed on the graphics screen by just scrolling down and clicking whichever one of these. And this is a useful thing that a lot of people don't know. They actually just changed the interface recently, so my slide is not up to date anymore. But it's the same thing. It's geopotential height. Now it's located as a drop down. So under the slider here, there's this where it says pressure isolines. Now it just says isolines, and you can click a drop down. You can have it show isolines and have the isolines be geopotential height. Geopotential height is what's showing these um, lines of kind of, you can simplify by thinking it's constant pressure. Technically speaking, they're the height. They're the height of the 500 millibar pressure profile, but we don't need to dive into that level of detail. You can just think of it as being the pressure lines. So you think of this as being lines of constant pressure. So where you see these lines go up, that's a ridge. Where you see those iso lines dip, that's a trough. So that's something that I do all the time. I slide this to 500 millibar, select geopotential height, and I just look at where everything is. And that's probably the primary thing I'm doing for long range forecasting. Then there's the RASP and the wind grams. So I talked about the RASP briefly, takes the NOM 12 and then refines it further. They used to have a 1.3 kilometer grid, which was the most the highest resolution model available to us, but within the last year, it seems that that stopped working. But there's still the 4 kilometer grid. To be honest, it's kind of a clunky interface to use. So I don't find myself using it as much. But if there's a lot of disagreement between the HRRR and the NOM, I'll often go to this as kind of like a tiebreaker, to kind of see, which one maybe has more credence. And then a lot of people are familiar with these wind grams. They're kind of useful. I find the wind grams especially useful for blossom. One of the limitations is that it's only at a point. So when I was talking about the point cast versus looking at the whole thing, you have a limitation because it's only showing you what's happening at that point. And one thing to note is they dropped the point in the wrong spot in Palomar. So don't use these wind grams at Palomar because it's not going to be very useful for you. But where does this data come from? It's pulling from the RASP. So this is just a special way to visualize the data coming from the RASP, and it just kind of tells, this looks like a pretty shit day of flying. We're kind of, I don't want to spend too much time because I want to get through material. It's almost top of the hour. So I'll just touch briefly. If you do have the like wind alert or iKite surf, you can look at the wind alert WRF. They don't do soaring parameters, but it is a very high resolution model. So if you wanted to corroborate what the winds were doing, it's a useful tool. And so if you're looking, a lot of people use wind alert to look at live winds. So when you're looking at, I know a lot of people use this for blossom. They look at one of the weather stations near blossom and they look at the wind forecast. So a lot of times that's pulling the wind alert WRF. And I know a lot of people swear by kind of what that model's reading for blossom to make their call. And what's interesting is they actually do have a 1 kilometer grid available, but it doesn't quite make it to San Diego. They really made it because they own iKite Surf and they market to kite surfers. So they're really making that for the Belmont Shore kite surfers. So not as many kite surfers in San Diego. There's Medio Blue. This is kind of more Euro, Canadian, UK. Got some Japanese models in there too. But really the problem is one, it doesn't have a whole lot of soaring parameters. They don't calculate top of lift for you or any of that stuff. But if you do want to see wind, clouds, precipitation, stuff like that, they got interfaces for that, and they have access to all sorts of models that we don't have access to in windy and XC skies. But the models that cover the continental US are generally the global versions of those models, which aren't as good as the GFS or ECMWF. So I don't find a lot of value in it unless I'm in Europe, because then you can get, the 1.3 kilometer resolution Icon D2 for forecasting where you're going to go fly in the Alps. Or some NEMs. They actually run their own models. So this actually is another service, private service that does run their own models. All these NEMS models are ran by MeteoBlue. What's interesting is Windy recently added NEMS Wind to the app, so you can access it. But it is their global NEMS model, which is a very coarse resolution. I think it's like 24 kilometer. So I don't find a whole lot of use for it unless I'm in Europe. Another tool is the soaring predictor. I mean, this is what I used when I was a brand new pilot and I didn't know anything about weather. Now that I know a bit more, I just don't really find this very useful. But where I do really find it kind of useful is for predicting places that are more ridge soaring oriented, so like Saboba or Torrey. But really all it's doing is pulling wind data directly from NOAA, so you could just go straight from NOAA to get the wind data. It's kind of a very simplified tool, which I get the appeal if you're a new pilot and you don't know anything about weather. You just want one number to tell you, if it's going to be good or not. But I haven't used it for a site call in years because I don't see a lot of value in it. Then there's NOAA. These guys are the experts. So they have all sorts of fancy graphs where you can look at what the winds and precipitation and stuff's doing. But the big thing I'll highlight here that I've already highlighted is these forecast discussions. So they publish these multiple times a day. I bookmark it for the San Diego area forecast discussion and just give this a read all the time. And then compare that to what you're seeing in your 500 millibar plots. Then there's the sounding. We're actually very fortunate in San Diego. So we have a weather balloon that goes up right next to Little Black. So there's not a whole lot of these that go up. I mean, I can't think of the exact number, but it's less than 100 balloons across the entire country. It's probably like 40 or 50 balloons that they send up for the entire country. We happen to have one right next to us. And they send it up twice a day. I believe it's at 4 a.m. and 4 p.m. standard time. And that's a balloon that has a temperature sensor, humidity sensor, and a pitot tube to measure wind speed. And then they publish that data into what's called a SKU-T. We don't have time to go over SKU-T, but this is a very good SKU-T. This is what we call an unstable day. And this is taking that balloon data. And so this isn't a forecast. Everything else that we're looking at, that we've looked at so far, is forecasts. Like the model might tell you that, the winds are going to be doing this at this altitude at this time of day. Who freaking knows? This is real data. So at 4 a.m., this is what the winds were doing aloft. This is what the temperature profile was aloft. This is real. So put more credence into that. A lot of the apps will let you generate SKU-Ts, like in Windy and XC Skies, you can generate a SKU-T. All those are going to be modeled, predicted, forecasted. They're useful, but only if the model is correct. And models are often wrong. And this particular representation here is comes from a site called Topa Flyers. Some pilots that wrote a script that formats the NOAA SQT data into something more useful for pilots. Because NOAA doesn't do this to help paraglider pilots soar. They do this to help them predict the weather. So they're looking at like the whole freaking atmosphere, and it's not very easy to see what's happening down low on those. So that just the interface here is easy. If you look at the NOAA site, it's like kind of like a little sliver at the bottom and you can't tell what's going on. But if you want to, you can look at the source from NOAA. I highly recommend the Topa Flyers, which is in the San Diego Club weather dashboard. So that's one of my bookmarks is the weather dashboard. And this is at the top of the dashboard. It's one of the, if you're going to go fly, especially winter, springtime, when there's instability is really what's driving your site calling decision. That's a good confirmation to check. Live wind readings. Like I said, everything before has been models. So pay attention to what's actually happening versus what was modeled. So there's a bunch of apps. My favorite is Wind Alert. It just has everything in a nice interface that's easy to use where you can see what's happening, click on any one of these stations, get more details. A lot of the club stations do pull through onto Wind Alert. I think maybe all of them. But the best interface for looking at the club weather stations is this Holfoy app. And you can bookmark all of the club weather stations and pull them up in Holfoy, see what's going on.
So that would be all of the club Holfoy stations versus the Joseph De Beer stations.
Oh, yes. Yeah, and I guess you have to go to the club dashboard now for the Joseph De Beer stations.
Yeah.
Right.
Yeah, so some of the Holfoy stations are still limping along if they're getting a signal connection. So it's really the 3G sunsetting. So if there's a 3G station that's still live and or a 2G station, those Holfoy stations will still be reporting.
Yeah, so right now Little Black works, Elsinore works, Horse works. But yeah, Palomar, Blossom, Laguna, they're down. But you can pull up Wind Alert and kind of see other weather stations nearby. Some of these you never know exactly where they are. They could be in a rotor, a Venturi, blocked, right? So that's why sometimes things don't always fully add up. So it helps to kind of know where the weather station is if you're going to put a lot of credence into it. But just pulling up a big visual, you can kind of see what's happening with the day. And then there's also MESA West. This is probably the most comprehensive, but it's kind of clunky. It takes a while to load, and but I think they have a lot more weather stations all aggregated into one place. Satellite and radar, very important thing to check, especially if there's clouds or storms in the forecast. You can see exactly where they are. There's so many apps. Pick your poison, find which one you like the most. Personally, I like using Windy. Got a nice interface, kind of all in one spot. But like really the source data comes from NOAA, and they have their GOES that you could look at to kind of view it straight from where it comes from. And I can't stress the importance of this enough. If clouds are in the forecast and you look out the window and you see clouds, check the satellite and the radar and compare that. Say you're checking at 8 in the morning, compare that to what the models are predicting and see maybe one model predicted the clouds correctly at 8 a.m. and the other didn't. Chances are, and if those models are saying two different things, chances are the one that predicted the clouds correctly in the morning is going to be more accurate, several hours later. because it has the correct heat loads applied. Another useful tool that we can't use anymore because of that sunset is the El Cap weather station had this solar sensor on it. It was really cool. I didn't get any screenshots of it before it went offline, but you could use it to tell when there was cloud cover at Blossom, because this red line would you know drop down, or you see it start to like chatter, right? Then it's like kind of scattered cloud cover. Um, and but if you saw a nice smooth curve, right, that thing's in full sun all day. It'd be kind of cool if we could get those in more places. Another kind of live thing that you can do is we got cameras set up places, not the club, but UCSD has cameras on a lot of our major peaks. So you can go to, it's called HP Ren. And it's great. One of the main things I like to use it for is to see how high the clouds are. Sometimes it doesn't help if, say Boucher Hill is in the cloud, you can't tell how high base is, but if you can see under the cloud from this camera, cloud base is at least 5,000 feet. And we have cameras other places. And Alert Wildfire had some really good cameras all around, but they went away. They still have some in Riverside County, but yeah, unfortunately, those don't appear to be active anymore. And then in the Windy UI, you can actually access cameras. Like some of them are actually like highway cameras, like on the road, but like you can kind of see if there's clouds forming. I need to plug in my battery. And then
So Rob's doing that. So I'll just mention that we do have links to the HP Ren cameras and kind of grabbing quite a few of the main ones to pay attention to. Under what's happening, the very bottom link under what's happening on the club website. So that's the webcams and SDHGPA XC route. So those what are the ones that are on that page are along the main cross country routes, along with the Palomar ones.
yeah, and I threw this one in just for good measure. Maybe somebody else will get good use out of it. But this is what the kite surfers use quite a bit. Down in La Ventana, there's a guy named Masviento, who's a retired meteorologist. And this is the primary tool he uses. Is they use satellite techniques to actually do live wind measurements along the ocean, but it only works along the ocean, so it's not as useful for us. But I've experimented with using it to confirm like how strong a Santa Ana might be, if it's going to be mild or moderate. This, you can tell this day it's pretty strong Santa Ana, but just briefly touch on that because I don't really use it that much. But all right, so then just to wrap up the forecasting here. So for long range, the big things I do is I read the NOAA area forecast discussion. And then I take note of any important patterns, right? So I'm looking at the 500 millibar. I'm looking for fronts, monsoons, Santa Anas, high, low pressure. I want to understand all that. And then, I'm looking at the winds, not only at the surface, but altitude. And then that gives me an initial glimpse of if it's going to be flyable and how good it might be. And if there's like a pattern coming, where it's, I can tell this day is probably going to be prefrontal. It gives me a good idea of some of the sight calls I might make. So yeah, the example here is Alex and I were trying to forecast when we were going to drive out to the Owens. And so, we're monitoring this, right? And just seeing stuff like breezy onshore winds, strong upper level low, right? That's not stuff that would make us want to go fly out in the Owens. So then intermediate term, once you get 2 to 4 days out, all of a sudden the NOM 12 becomes available. And then you also have the GFS to corroborate against. So you can kind of flip between the NOM 12 and the GFS and XC skies. And this is kind of our first real glimpse, other than like just seeing the patterns and kind of knowing this pattern generally brings good flying, or this pattern brings bad flying. You can start to see what the actual tops of lift and actual winds will be, and really get an idea of where you might want to fly. But a lot can still change. These are still all fairly low resolution models, forecasting a decent time period in advance. So you really can't make a solid call until like the night before. So this is looking at the Owens Valley, and it's very clear, when we were looking at this one day in September, this is a no-go. Whereas this day in early October, this is looking promising. So this is where we started. This is where we started making phone calls of, who can drive retrieve, who's going to be willing to, drive 6 hours, go camp a weekend and drive around in the desert for hours to go pick us up. Once we start seeing this. And then short term. So unfortunately, it'd be great if we could get this information further in advance. Anybody's, wives, girlfriends, I'm sure feels the pain when they're trying to nail you down to make plans for the weekend. But unfortunately, it's very difficult to really make solid plans until 1 to 2 days before. And that's when we get these high resolution models, the NOM3, HRRR, and sometimes I like to use the RASP. All of those models become available. In general, what I find, and a lot of people agree consensus-wise, is the HRRR is usually more optimistic about the top of lift, and the NOM3 is more optimistic about the wind strength. And the reality is you probably get the worst of both. So kind of the general rule of thumb is, if you want to oversimplify things, take the altitudes you see on the NAM and the winds that you see on the HRRR. And I mentioned this already before, if the NOM and the HRRR disagree, you can use the RASP, or you can access the RASP via the wind grams, right? And use that as a tiebreaker. And to be honest, I've shown up on some days that the soaring kind of shit the bed, and I've had great flights. Sometimes just go to no. But in general, you want to see high top of lift, light winds, no high clouds, and some scattered cumulus are nice if they're not getting tall enough to OD. But like I said, you don't get perfect forecasts every day. So if you want to fly, as long as it's safe to fly, go fly. But it helps to try to put yourself in the best spot for the day. So the images here are kind of a dream come true. On this day, we got up to 17,999 feet for 7 hours and did the classic Owens Valley flight. And that's a picture from this day. All of that was forecasting. So don't forget morning of, you got to confirm all model predictions. Things can change dramatically even overnight. Check the morning update. The models could have looked really good when you went to bed at 10 p.m. and then you wake up in the morning and no longer the case. Check the morning sounding, check the live winds, check the satellite, the cams, the radar, and then make your final sight call. And I think we're pretty much out of time. I don't know if it's worth continuing, Steve. Maybe we should just break it here and then maybe just do questions on the material that's been covered thus far.
Yeah, I think we saved the site-specific slides
Yeah.
for another day.
Yep. Agreed.
Yep, there's a
So
lot of good content there. And big thanks to Rob. A lot of good clapping hands there. Most people are muted, but um, great job, and super great to see that you've been collecting all this data for a long time. There we go, all the clapping hands symbols there. So
yeah, so I guess at this point, I don't have a hard stop. So if anybody wants to get to bed, start getting ready for bed, I won't be offended if you drop off immediately. But if anybody does have questions and wants to kind of ask, go ahead and ask away.
yeah, so just reading through the chat, there was really only one question, and so SkySight is a paid subscription similar to XC Skies. I believe that SkySight's using the European models, so it does cover North America, but I don't believe, or you would need to make sure that it has the HRRR and the
Yeah,
NAM
I'm
3 to
not
make it
familiar with
worthwhile.
Sky Site at
Yeah,
all.
yeah.
But I know for those that want to go fly in Europe, I think I saw, I don't know if Flo's still on the call, but he's you know, came from Europe, and Jerome also. They might chime in, but from my trips to Europe, it sounds like most of the locals are using Burn Air. So there's an app called Burn Air that pulls in a lot of the European models, and they actually do some very cool algorithms to like tell you what region of the Alps is going to be good at sea. That seems to be what most people are using. But Burn Air doesn't do anything in North America. Any other questions? I guess it all made complete sense.
Without going into a deep dive, could you pull up that SKU and just kind of explain to me why that first one is a perfect? I still need to learn about these.
So let's see, that was back here. Yeah, so the the SKU shows temperature as a function of altitude. So this red line right here, that's this is the temperature that the balloon measured as it went up. So on the x-axis, we have the temperature, on the y-axis, we have the altitude. So you can see generally as we're going up, the temperature is getting colder. And that's important because when a thermal rises, you know, the sun heats up the ground heats up a puddle of air. Eventually that air starts to rise. So that air starts to rise a certain amount hotter than the surrounding air. That's why it rises, because of its buoyancy. But as it rises, it expands adiabatically, so it cools. So as the thermal rises, it cools. And that thermal will rise until the temperature of the parcel of rising air matches the temperature of the surrounding atmosphere. So what you want to see is the atmosphere get colder as a function of altitude. So the the more the atmosphere, the more slope to the left the red line here is, the more what we say is unstable the day is. And what these yellow lines are, these are what are called the dry adiabats. So these yellow lines are kind of the slope that the thermal would cool at. So what you can do is you can look at the x-axis here, and you can find like what the high temperature for the day is at the site that you're at. And say on this day it was going to get up to 63 degrees, right? You could find 63 degrees on the x-axis here, and then follow one of these yellow lines. Draw a line parallel to the yellow lines. Where that intersects the red line, that's going to be the top of lift. Well, it's going to be the thermal height, which
just drew a line on there for you. So
Yep.
yeah, so if you look at the dashboard, there's a reason why we have the NOAA forecast for the day right next to it. So what I do is, and encourage people to do, is to look at the high temperature for the day. That's going to be the picked image over on the right, and then draw that onto, or visualize if it's going to be roughly 60 or whatever, and then you want to follow or parallel along the dry adiabatic rate lapse rate lines, which are these orange yellow lines. Follow it up until it intersects with that red line there, and then draw across, and that's going to be your maximum height for the day. So these are in altitude. And then anticipate that this overall lapse rate red line is going to heat and raise throughout the day. So typically I draw it across where it hits and then give it an additional 500 feet for the heating or rising of all of that from the 4 a.m. or 6 a.m. Weather balloon that went up. So all of that air is going to heat, everything's going to rise. So what you're going to see though is this area here is an area where there's inversion. So in this case, if it was getting to 65 or so, you would be then coming up to about 4K, roughly about here. And so that would be the max of the day before you hit an inversion layer.
Yeah, and keep in mind, the further inland you go, generally the higher the the temperatures reach. So that's one of the reasons why Marshall often will work, kind of better in the summertime, just because the the desert out there gets pretty darn hot. So it can oftentimes rise up through some of the inversions.
Yep. So this balloon or real-time data is collected at Miramar. There's also one out in Arizona, and then the next other one close that's in California is Edwards
Santa
Air Force
Barbara,
Base.
right?
No, Edwards Air Force Base is
Oh.
the next closest one. And then also for the Owens, there's one, the closest one is oh shoot, is out of Reno. So that's not really the same, kind of the same air mass, but it's outside of the main Owens Valley area. So, but that's the closest one.
Yeah,
to
and
the Owens.
one thing I want to highlight is the Topa Flyers view here is super nice because they give that middle graph there that shows the lapse rate. And essentially what that is, that's just showing what the slope of the line is. So it's in degrees per 1,000 feet. So you can see very easily that this is a very good sounding, because it's 4 degrees per 1,000 feet all the way up to 3K. And then it makes the inversions very clear, right? You can see right at about 4,000 feet on this sounding that the lapse rate goes negative. And so a negative lapse rate is an inversion by definition. So yeah, this view just makes it so easy to see where the unstable and stable layers are.
And then it also shows you the the wind speed at altitude.
Yeah, and then one more thing that we didn't touch on yet is what the green line is. The green line's the dew point. So where the green line touches the red line, you can expect there to be clouds. And you also notice that they put a blue line there. That's saying that cloud base is going to be there. And then but you can see that higher up, the green line does hit the red line again at about 8,000 feet. So on this day, you might expect that maybe there's going to be a layer of high clouds at 8,000 feet, maybe blocking out some sun. But that's also at, 4 in the morning. A lot can change. Any other questions?
All right, I think that's probably
Or they're all
covers
sleeping.
most of it. Yeah. All right. Again, big thanks to Rob for pulling this all together, and we'll do it again.